Our next speaker is Francis Jan Cyr-Racine from Harvard. He'll be telling us about small-scale dark matter structure. Okay.
All right. All good? All right. Thanks for the organizers for allowing me to speak in this plenary session and share some of the recent work I've done actually with the people listed here. So in dark matter science, and as a community, we kind of hope for the best. So we hope that we can actually find whatever that stuff is made up, either in the lab, at direct detection experiment, or maybe produce it at colliders, or even kind of find some signatures of its either decay product or annihilation product in a high energy observatory. But in a lot of the work that I actually do, I kind of prepare for the worst. That is, what if dark matter is actually dark? And the only tools that we have to actually study its properties is astrophysics. Now, I want to remind you that everything we know about dark matter and the universe actually comes from either cosmology or astrophysics. So this is, of course, a reasonable thing to do, to ask the question whether astrophysics can provide even more information about the nature of dark matter. Fortunately, there are lots of probes that we can use in order to probe the physics of dark matter. Things like gravitational lensing, of course, the studies of dwarf galaxies within the local group, studies of gaps within stellar stream, which is a growing industry right now, merging clusters, and studies of the Lyman alpha forest, can all actually provide some useful information about the nature of dark matter. Now, if you go down this route of using astrophysics to learn about dark matter, the first question you want to ask is, what kind of physical properties of particle dark matter can you actually learn through astrophysics? And of course, there are many possibilities, but in the work I've done in the last 5 years or so, I kind of focus on two broad possibilities here. One thing you can probe is the physics of dark matter that was active in the early universe when the density fluctuation in dark matter density fields were more or less in the linear regime, and the properties, the physical particle properties of dark matter could have a sizable effect on the evolution of these linear structure. For instance, a typical example is the existence of warm dark matter, which can wipe out structure on small scales, or maybe the coupling of dark matter to some relativistic species gives rise to these kind of acoustic features in the linear matter-power spectrum. The second thing that you could try to probe with astrophysics is the presence of physics that actually affect the structure formation at late times, very close to us today. And kind of the poster child example of this is the presence of self-interaction in the dark sector, which affects the very small scale structure, might create cores in galaxies, and small scale halos, for instance. So the reason why we can actually probe these broad categories of physical processes I've just described to you is because they actually impact structure on small scale in quite a significant way. So these are simulation that Mark Vogelsberger ran with some of these models that I was showing you on previous slides of a Milky Way type galaxies. And you can actually see just by eye that, of course, as you change the linear physics in the early universe, the impact on structure formation at that time is quite obvious. You tend to form less structures if you have some kind of cutoff in the matter-power spectrum, for instance. So this is kind of effect we like to look for in galaxies. And of course, also the presence of self-interaction within the dark sector also affects the density profile of these subhalos. So these are the kind of things that you want to look for using astrophysics. So the tool of choice for me, for the work that I'm doing, in order to study this kind of small-scale structure that may hold key information about the particle nature of dark matter is strong gravitational lensing, and especially on galaxy-scale gravitational lenses. That is where you have a massive galaxy that actually multiply imaging a background source. It'd be either a quasar, or maybe another galaxy, or maybe a dusty star-forming galaxies. So there's a whole zoo of possible gravitational lenses that you can use in order to study the small-scale subhalo contents of these lens galaxies in order to learn something about the physics of dark matter. Of course, this is like some of like an older topic. It's been around for some time, starting from the pioneering work of Dalla and Kuchenek. But more relevant to what I'm going to be talking about today is this, essentially this gravitational imaging. So here, essentially what you want to do is, if you have a background galaxy that's actually gets strongly distorted by a foreground galaxy, so you get these kind of lens arc, and you do a detailed study of the surface brightness map along these lens arcs in order to find, directly detect subhalos along the arcs. This is what Simone Vighetti has done in this Nature paper. He found some evidence for, say, a 10 to the 9 subhalos within the lens galaxy. So that's one way to do it. You can also do it with interferometry, with the ALMA data, where essentially this is more or less the same story, where you look at detailed surface brightness map along lens arc in order to find the presence of possible dark matter substructure. So just want to kind of advertise this. So we have, at Harvard, we have actually developed some in-house tools to tackle this problem in a more consistent statistical way. And this is work led by Tansu Dalen, which is actually here. And unfortunately, I won't have time to actually talk about that. But I invite you to talk to him to get more detail about this. So what I actually want to talk about today is kind of a different approach to probe dark matter, small-scale dark matter structures using gravitational lensing. It's kind of using a different language, kind of moving away from this language of just talking about individual subhalos or lensed that appears in projection close to lens arc, but instead just talk about the two-point correlation function of the dark matter density field along some strong lensing region. So this idea was actually introduced by Isabelle et al. A few years ago, and they show in this paper using a forecast of ALMA data that you can actually go and look at detailed surface brightness at the surface brightness along these lens arc and try to extract this two-point correlation function of the dark matter density field, and they made some Fisher forecasts for what you could measure if you had enough signal to noise. So the story here essentially is that so you have some lens galaxy which has a lot of substructure into it, and the light for the foreground galaxy is going to go through it in order to reach your telescope. But as it goes through the lens galaxy, it actually encounters a lot of small-scale structure, and each of these small-scale structures gives rise to little deflection as it crosses the lens. But you can imagine that if you're adding a very small number here, the statistics, the perturbation at the ends are close to Gaussian because there's something like a central limit theorem actually kind of kicking in because you get perturbed small perturbation, but a lot of them, essentially. Of course, this is not always true. It depends on what the exact dark matter physics is. If you have kind of strong cutoff in the matter power spectrum, you end up with only a few deflection. The statistics are non-Gaussian. So there's a way to try to distinguish these two scenarios here. So my philosophy here is that, okay, so in a realistic lens galaxy, I mean, the lens galaxies, of course, complicated objects, they have a lot of structures into them. And in reality, the convergence field of the projected surface mass density of dark matter subhalos is probably not entirely Gaussian. But it doesn't mean you should not try to look and measure it and try to learn something about dark matter, even though it might not contain all the information about the dark matter density field. Now, the key question you want to ask is, if you go and try to measure this two-point function, what will you learn about low-mass subhalos from measuring this power spectrum? So in a recent paper led by Harvard student Ana Diaz-Rivero, we actually tackled that question and try to answer what are we going to learn from about dark matter from looking at this power spectrum. So we did the simplest thing we could think of is start from the halo model and compute from first principle what is the convergence power spectrum that you expect in a typical lens galaxy. So this is kind of a standard calculation. If you're familiar with large-scale structures, this thing has been done with a large-scale structure like a long time ago. It's essentially applying the same kind of philosophy, but in much, much smaller scales. And essentially, when you compute this volume average two-point function, and of course, we're interested in the power spectrum, which is just a Fourier transform of that. So as a warm-up, so we'd like to understand, so if you have a population of subhalos within the lens galaxy, there are just NFW, that NFW density profile, or rather truncated NFW, since they're sitting inside this host and you get truncated by tidal interaction. So this is the density profile. And then we'd like to ask the question, what does the power spectrum actually look like with such a population of subhalos? So here's the answer. And the interesting thing here is that there are actually three key features of this power spectrum. So this is a power spectrum as a function of wave number. Notice this is actually kiloparsec inverse, so we're probing typically kiloparsec scales here. And there's essentially three features. So at low k here, this is kind of constant plateau, a constant amplitude. And it's essentially you're probing scales that are much bigger than any subhalos within your lens galaxy. So for you, at these scales, all of these subhalos look like a bunch of point masses, and then you're Fourier transforming that, and the Fourier transform of a field of point masses is essentially just white noise. It's a flat power spectrum. And the exact amplitude of that power spectrum essentially depends on the kind of average abundance of subhalos within the lens galaxy, which is encoded as kappa sub, as well as some moment of the subhalo mass function, which of course are important. So as you move to smaller scale here, you have this turnover. And essentially what happens is as you move to smaller scales, you start probing the inner density profile of these subhalos. So you have this turnover. And this turnover exactly corresponds to essentially the truncation radius of the largest subhalos within your lens galaxy. So as you keep moving to smaller scale, essentially at some point you reach this asymptotic regime where the power spectrum is asymptote to a constant power law, which for NFW is exactly 1 over k to the fourth. And that just reflects the fact that NFW have 1 over r cusp in the middle, and then you project to do the lensing, and then you do the Fourier transform, you get something that exactly goes as 1 over k to the fourth. So this is for kind of standard CDM, and then we ask the question, say, what if I put non-trivial dark matter physics? What if I turn to, say, a self-interacting dark matter? What does it look like? So let's just put a chord profile now, which we're going to use a Burkhardt profile here, and this is illustrated in the green line here, and then compute the power spectrum for these kind of theories. So this is what it looks like. Here I'm actually comparing what I had before for the NFW, which is shown in blue here, to now this kind of chord profiled power spectrum here. And you see that actually on larger scales, more or less looks the same. It's not surprising. There you're kind of probing the broad distribution of subhalos within the lens galaxies. But as you go to smaller scale, you see kind of a change of slope here. And that really reflects the fact that the inner density profile of a CDM subhalos versus CDMs actually look different. They have different inner density slope. And you see this reflected here, where actually the chord profile is exactly 1 over k to the eighth compared to NFW, which is 1 over k to the fourth. So of course, the largest difference here is at these small scales, which, given this is in kiloparsec, this corresponds to scales of 10 to 100 parsec. So this is an insanely small scale, of course. And if I just want to put what Izave et al. Forecasted for their sensitivity and scale, see that it's more or less sensitive to these range of scales, which is where the subhalos between the NFW, the Burkhardt profile, are actually very similar. So it's slightly disappointing that it might be actually really hard to get to these scales. And that's not really surprising, because you imagine these are lens galaxies at redshift half, and you have to probe scales of like 100 parsecs of something that's a redshift half. It's definitely a challenging measurement. So where we started in collaboration with Chuck Keaton and Leonidas Moustakis is try to determine what do you need? What will you need to actually measure such a thing in reality? So we started a simulation program where we actually use some of these theoretical results that I was showing you before for the shape of what this power spectrum should look like, and essentially just kind of generate realization of that power spectrum. So this is just a convergence map for the power spectrum. And of course, what you care about for the lensing is the deflection field, which is shown in these little arrows here. Of course, it's much smoother because it's related by Laplacian. And then you generate kind of synthesis images and try to extract what the power spectrum is from these images. This is a nice Einstein ring with some light from the lens galaxy here. And just to kind of show you which kind of effect we're talking about here, what's the kind of magnitude of perturbation we're talking about here. So this is actually the image residuals. Of course, I can do that because I know exactly what went into creating these images. And you see that we're talking about essentially a sub% effect on the surface brightness map of these lens galaxies. So these are kind of subtle surface brightness variation that are caused by having non-trivial substructure within these lens galaxies. So we've developed power spectrum estimators that takes in images from these lens galaxies and try to measure what this power spectrum it is. So this red line is whatever I had for the truncated NFW case. And these error bars is what our estimator actually returns if you try to fit this power spectrum with 3 different momentum wave number bins. And you see that actually the signal is there. So this is very encouraging. So it shows that in practice, we could actually try to pull that signal out of lens images and try to learn something about this behavior here at large wave number, try to determine, try to probe the inner structures of subhalos within the lens galaxies. Of course, we can also detect the amplitude. So this is kind of exciting. So substructure lensing is actually one of the best ways to study small-scale structures at cosmological distance from the Milky Way, getting key information about dark matter physics. So I think the endpoint function is actually quite interesting because it kind of moves away from the language of individual subhalos, and it allows to capture more general density fields within the lens galaxies. As we just discussed, the power spectrum mostly depend on the abundance of substructure, some tidal truncation physics inside the lens galaxies, as well as the inner density profile of the subhalos. In principle, it looks like we should be able to pull out that signal in realistic systems, and we're actually doing a thorough study of what you need to measure something interesting. Thank you.
Okay, thanks, Francis Yen. Do we have any questions from the audience? We have time for a couple questions.
I think we have David there.
Yeah, hi. Thank you. So this is very interesting. I'm curious, you did this sort of toy study with some images of these lenses, and from the residual, you extracted essentially this power spectrum measurement.
Yeah.
As someone who's unfamiliar with these details, can you just explain exactly how you get the residual? There must be some assumptions that go into it about the original lens system. Can you reliably extract those sort of in situ?
So, I mean, I mean, these are synthesis image. So I know exactly when went in. I know exactly what's the lens, the life in the lens galaxies. I know the broad lens model, like the macro model. What's the density profile of the lens galaxy itself before I put more subhalos into it. So here, I mean, this is really to show you the actual effects. So I just subtracted everything else that I know already in order to show you what do the substructure actually do on the lens, just to show you kind of the magnitude. This is order 1. This is order 10 to the minus 3.
So basically, the sort of macroscopic features are enough to get the residuals, case by case, without any particular assumptions.
So what you do in practice is that you fit everything at the same time. So you fit for the broad model of the lens. So there's like 30 parameters. You have to fit for the light of the lens galaxies. So you fit all of these at the same time, as well as the amplitude of the power spectrum. So these are kind of big Monte Carlo fits essentially you do to these lenses. Yeah.
So really, there's no barrier to doing any of this now. You just need the catalog and run it all through the machinery, right? Or what's left? Like what's?
Sorry?
Sorry, it seems like if you have the catalog, you can just go do it. Like, is there anything that's
Yes.
missing in particular? Or?
So I mean, you could do it. You could do this with real data right now. So what's missing here is kind of realistic source modeling. So the source of real, I mean, here the source that gives rise to this Einstein Ring is just like a simple elliptical galaxies. But in practice, real lenses have kind of more complicated source morphology. So you have to kind of use a more complex source model. But that's essentially, this is the same thing, but just adding more bells and whistles to the model. Yeah.
Okay, I think we're going to have to cut things off there. You can talk to Francis Yen offline. All right, let's thank him again.